Bismillahirrahmanirrahim. Assalamu alaikum dear students. Today is our 23rd lecture of Discrete Structures CSC 102. In the previous lecture we were discussing sequences, alternating sequences, summation notation, product notation and their properties. Due to the shortage of time, we haven't discussed change of variable and factorial notations, and I have told you that we will discuss these two topics in the next lecture. So today first we shall discuss these two topics, change of variable and factorial notations, and then we shall start mathematical induction. So in the previous lecture we have discussed summation and product notations. Now today, what is the change of variable in the summation and product notations? Observe that if we are given summation k from 1 to 3 k square is equal to, basically if we open this summation we will get 1 square plus 2 square plus 3 square. And also if we open this summation where I is from 1 to 3 I square, if we put I is equal to 1 we get 1 square, if we put I is equal to 2 we get 2 square and 3 square, and sum of these three terms. You can see the result of these two summation is equal, whereas in the first summation we have used k from 1 to 3 k square, and in the second summation we have used I is equal to 3, I is equal to 1, 2, 3 and I square. These two summations give us the same expanded form of the summation. So we can conclude that the symbol used to represent the index of summation can be replaced by any other symbol as long as the replacement is made in each location where the symbol occurs. Means if we replace k by I here, we have to replace k by I here also. So we have to replace the index of the summation at each location. If we replace the index of summation at each by any other index I, j, k, l, m, n, o, p, any other, we use any other index, we have to, if we change it at every location where it is used, then the summation will not be affected. As a consequence, we can say that the index of the summation, as a consequence we can conclude that the index of the summation is a dummy variable. Dummy variables mean that we can replace it with any other variable, the result or the resultant will be same. A dummy variable is the symbol that derives its entire meaning from its local context. Out of that context, the symbol may have another meaning entirely. Means here we can use any variable. The variable the variable doesn't matter here. If we use k here we get the same answer, if we use j here we get the same answer. So such variables in the summation are basically called dummy variables. Now, how to transform a sum by change of variable? If we are given a sum, for example like this, summation k from 0 to 6 1 over k plus 1, this, we can change the variable and we can alter the entire summation. For example, if we want to change the variable here k into j, we put this substitution, we use this substitution, we put k plus 1 is equal to j. In this case we have to look at each limit, upper limit, lower limit of the summation, and also the expression which is used in the summation, which we have to sum. First we calculate the lower limit and then upper limit, and then we change the expression in the summation. So when k is 0, the lower limit is k is equal to 0. So when k is 0, if we replace k plus 1 by j, then if we put 0 here, then j becomes 1. Now the upper limit, if we use k is equal to 6, then here by substituting k is equal to 6, then j becomes 7. So in this summation, the lower limit and upper limit has been changed. In this case, now the summation will be j from 1 to 7. Now we have to change the expression which we have to sum. Thus the new sum goes from j from 1 to j is equal to 7. Next we calculate the general term of the new summation. You'll need to replace each occurrence of k by an expression in j. So here we have k plus 1, and instead of k plus 1 we have to use j. Or you can say that you can do it like this: instead of j, you find the value of k from this expression, where we can write k is equal to j minus 1. Now put here in the denominator here, instead of k, put here j minus 1. We get k plus 1 is equal to j minus 1 plus 1. 1 is cancelled with 1 and we get j. So 1 over k plus 1 basically has been changed to 1 over j. So the whole summation here, this has been changed now to this form: summation j is equal to 1 to 7, and the expression, the general expression is, general term is 1 over j. So this is how we can change the variable in the summation, but we have to take care about all the terms of the summation, means lower limit, upper limit, and the general term of this summation. We have to change the variable in each place, or in each occurrence where this index occurs. Another example of this change of variable is that if we are given such type of summation and we have to make this change of variable in this expression, and here the upper limit is used here, n, in the expression. In this case, what we do, we follow the same process to change the summation into a new variable. When k is equal to 1, we have to change the lower limit of the summation, and then upper limit, and then the general term of the summation. When k is 1, we have to, then j is equal to 1 minus 1, 0, because we have j is equal to k minus 1. When k is n plus 1, then what? And j is k minus 1, means j is equal to n plus 1 minus 1, which gives us n. Here you can see this. So the upper limit is now n, since j is equal to k minus 1. Now from this expression we have to find the value of k. From here we can write k is basically j plus 1. Now in the general term, which is given as k over n plus k, we replace k by j plus 1 in the new numerator and in the denominator. So we obtain this. So the new general term of the summation is this. So the whole summation k is equal to 1 to n plus 1, k over n plus k, becomes summation j from 0 to n, because lower limit has been transformed to j is equal to 0 and upper limit transformed to n, and the general term of this summation has been transformed to j plus 1 over n plus j plus 1. So this is how we can transform a summation by using a change of variable to a new form of the summation. Here, if we open up these two summations, the result will be same. The expanded form of both summation will be same, but just sometimes we have to simplify, we have to change the summation to simplify our problem, and to, you can say, to solve our problem, we need somewhere the change of variable. So we can, this is how we can make the change of variable in the summation. Once again, we have to change the lower and upper limits also. Now the B part of this exercise was this: transform the summation obtained in part A by changing all j's to k's. And then here, as we have discussed in the earlier slides, that we can change the index to any other index by changing the index at each occurrence of that index. So we can now change j's to k's. Here we have j, j, j. Now we change j to k at each occurrence. So this becomes, in here instead of j we write k, here we write k, and here we write k. So this again becomes this. Now combining this and this equation, we can write this. Now still we have, in both expressions, on left hand side and on right hand side, we have the same index variable, which is k, but its lower limit, upper limit here and lower limit, upper limit here are different. Its general term here and here are also different. But if we open up these two summations, if we write these two summation into expanded form, the resultant will be same. So this is how we can make the change of variable in the summation notation. The next is the factorial notations. What is the factorial notation? We shall discuss the significance of this factorial notation when we shall study the counting and probability. In this lecture, we shall only discuss what is factorial notation and how we calculate different factorials. Now, by definition, for each positive integer n, the quantity n factorial denoted by n factorial, n and this sign, this basically denotes the factorial of the integer n, and read as n factorial, read as n factorial. This number is basically defined to be the product of all integers from 1 to this number, from 1 to this number. Means n factorial is equal to n into n minus 1 into n minus 2 into n minus 3 and so on up to 3 to 1. For example, if we have 5 factorial, then what does it mean? 5 factorial means 5 into 4 into 3 into 2 into 1. This is, if we multiply these numbers, 5 4s are 20, 3s are 60, 2s are 120. So 5 factorial is basically 120. Another expression which you have to memorize, 0 factorial is always 1. There's a proof of this. 0 factorial is equal to 1. There is a proof in mathematics. We can prove it that 0 factorial is 1, but here I'm not including the proof of this. You can see in any book of discrete mathematics, the proof is available that 0 factorial is always equal to 1. A recursive definition of the factorial can also be given like this. N factorial is basically, if n is 0, then 0 factorial becomes 1, and if n is greater than or equal to 1, then we can write n factorial is equal to n into n minus 1 factorial. For example, if we are given here 5 factorial, then we can write it as 5 into 4 factorial. This may be equal to 5 into 4 into 3 factorial. This may be equal to 5 into 4 into 3 into 2 factorial, and so on. At the end we can write here 1 factorial. 1 factorial is always equal to 1 because 0 factorial is 1 and 1 factorial is also 1. So the next example illustrates the usefulness of the recursive definition for making computations. The first 10 factorial is basically here I have given 0 factorial is 1, 1 factorial is also 1, 2 factorial is 2 into 1, 2, 3 factorial is 3 into 2 into 1, which is 3 2s are 6, 4 factorial is 4 into 3 into 2 into 1, which is 24, 5 factorial is 120, 6 factorial is 6 into 5 into 4 into 3 into 2 into 1, which is 720, 7 factorial is this 5040, 8 factorial is 40,320, 9 factorial is 362880. Now, how to compute the factorials, how to simplify the factorial expressions. Simplify the following expressions in this example. 8 factorial over 7 factorial. How we can simplify this expression? We have to use the recursive definition of the factorial, which is given here. This will simplify our calculations. So 8 factorial over 7 factorial. By using the recursive definition, we can write 8 into 7 factorial divided by 7 factorial. Now 7 factorial cancel, we get simply 8. So by using the recursive definition of the factorial, we can simplify easily the expressions which involve factorials. Similarly, the B part, we can simplify it easily. 5 factorial, we can write it as 5 into 4 into 3 factorial divided by 2 factorial into 3 factorial. So I have stopped it up to 3 factorial because 3 factorial is here greater and 2 factorial is smaller, because if I simplify the greater factorial of a number, it will simplify our calculations. A 2 factorial is 2 and 2 2s are 4 and 5 2s are 10. So we can simplify the expressions which involves factorials by using this recursive definition of the factorial. Similarly, we can simplify this. On the next page, I have given the solution of all these exercises. Here you can see that in C part, 1 by 2 factorial into 4 factorial plus 1 over 3 factorial into 3 factorial. Here we can write, here we have 4 factorial, here we can write, here we have 4 factorial, we have multiplied and divided by 3, so that here 2 factorial becomes 3 factorial. Here we have 2 factorial, here we have 3. We have written it as 3 into 2 factorial, which is 3 factorial. So here we have written multiplied 4 by 4, multiplied and divided by 4 by 4, and then 3 factorial into 4 or 4 into 3 factorial can be written as 4 factorial. Now this becomes 3 factorial, 4 factorial, this becomes 3 factorial, 4 factorial. Now we can take the LCM 3 factorial into 4 factorial. We can easily simplify this. 3 plus 4, 7. Now this becomes 7 by 3 factorial is 6, 4 factorial is I have given here 24. Now 6 into 24 is 144. So we can simplify the factorial notation like this also. Means we can make factorial notations has accordingly by multiplying and dividing by the same numbers. Similarly, the D part was here the n plus 1 factorial over n factorial. We can immediately simplify it. N plus 1 factorial can be written as n plus 1 into n factorial. So n factorial is cancelled out with n factorial. We get n plus 1. Similarly, here in the part E, we have on the numerator we have n factorial, and in the denominator we have n minus 1, n minus 3 factorial. The upper factorial can be reduced up to n minus 1, n minus 3 factorial. So n factorial can be written as n into n minus 1 into n minus 2 into n minus 3 factorial. So this can be cancelled out with this. We get this. So we can simplify the factorial notations like this. Some special cases of factorial. We shall again discuss the significance and meaning of this factorial notation in the counting, but here I am just giving you the idea how to simplify and calculate such type of expressions which involves factorials. Let n and r be two integers, any two integers where r must be less than or equal to n, and it must be a positive, or you can say non-negative integer. Both of these must be non-negative integers. Then the symbol n, r, and with the parenthesis brackets, the brackets like this. This can also be denoted as NCR. This is also called NCR or N choose R. The symbol this is read as N choose R or NCR. C is for choose, N choose R, and represents the number of subsets of size R that can be chosen from a set with n elements. So I again repeat, this is basically N choose R or NCR, represents the number of subsets of size R that can be chosen from a set with n elements. For example, if we have set A which contains 3 elements, 1, 2, 3, then how many subsets of size 2 can be chosen from this set of 3 elements? We can make 1, 2, we can make 2, 3, and we can make 1, 3. So we can make 3 possible subsets of 2 elements of this set. If we calculate NCR, how many elements are in this set A? 3. And C, R. R is we have chosen 2 because we have to calculate number of sets which can be chosen from this set of 3 elements. If we simplify this, we get 3. How we get 3, I shall explain you later. So we can choose 3 subsets of this set which have 2 elements. So there are 3 possible subsets of size 2 which are the subsets of this set of size 3. Size 3 means it has 3 elements. So this number n choose r or NCR represents the number of subsets of size r that can be chosen from a set with n elements. So how to compute this number? How to compute this number? This is basically a formula which is NCR or n choose r is equal to n factorial divided by r factorial into n minus r factorial. For example, if we have to simplify this, 3 choose 2 or 3 CR is basically 3 factorial divided by 2 factorial into 3 minus 2 factorial. So this is basically 3 factorial divided by 2 factorial into 1 factorial. If we simplify this, just we have simplified these expressions, we can immediately obtain 3 into 2 factorial divided by 2 factorial into 1 factorial. So 2 factorial and 2 factorial cancel, 1 factorial is 1, so 3 by 1 is 3. So from this set of 3 elements we can take 3 subsets with 2 elements. So this is basically the n choose r or combinations. We say it also the combinations or NCR, and we can calculate the all possible subsets of size r that can be chosen from a set of size n, can be calculated by using this formula. Now computing NCR by hand, we have to compute 8C5, 8 choose 5, 4 choose 0, n plus 1 choose n. We have to calculate just to show you how we simplify such type of factorial notations or expressions. We can write 8C5 by 8 factorial over 5 factorial into 8 minus 5 whole factorial. So this is equal to what? This is equal to 8 factorial divided by 5 factorial into 3 factorial. So there is another method of simplifying it. That one method is this, that expand or open up this factorial up to this factorial, then cancel out these 2 factorials and we can simplify the other 2 terms. One method is this, that open up expand all the factorials just like this: 8 7 6 5 4 3 2 into 1, and 5 into 4 into 3 into 2 into 1, and 3 into 2 into 1, and then cancel out the same integers. 5 can be cancelled out with 5, and 4 can cancel out with 4, 3 with 3, 2 with 2, and 3 into 2 is 6, and this can be cancelled by 6. So we get the answer is 56. So what does it mean? If we are given a set of 8 elements, then we can make 56 subsets of this set of 8 elements, 56 subsets with 5 elements. The next is 4C0. basically here here I have written 4C0, and here I have calculated 4C4. So this can also be calculated like this. 4 choose 0 is basically 4 factorial over 0 factorial into 4 minus 0 all factorial. 0 factorial is 1, as you know. 4 minus 0 is 4, so 4 factorial can be cancelled out with 4, and we get 0 factorial, and here we get 1. 1 by 1 is 1, so 4C0 is 1. Similarly 4C4 is also 1, as 4 factorial over 4 factorial into 4 minus 4 is basically 0 factorial. 4 factorial can cancel out with 4 factorial, we get 1. Now we have to calculate this. which is n plus 1 c n, and this can be written as n plus 1 whole factorial into n factorial and n plus 1 minus n factorial. N is cancelled out with n. Here we get 1 factorial, and here we have n factorial, n plus 1 factorial, and this can be here cancel out and we get n plus 1. So this is how we can simplify this factorial notation, or this combination NCR. So these were the topics which we had to discuss in the previous lecture, but due to the shortage of time we have discussed these topics in this lecture. The next we start the mathematical induction 1. In mathematical induction we shall study principle of mathematical induction, what is the method of proving this principle, and then we shall try to discuss finding terms of sequences, sum of geometric series, and some other related topics. Now, what is the induction? A little bit introduction to the induction. Basically, mathematical induction or principle of mathematical induction is a method of proof. It's a method of proving the statements of general statements. For example, a statements like this: any whole number of cents of at least 8 cents. Basically here this is the notation of cent, this 8 cents can be obtained using 3 cents and 5 cent coins. Basically cent is a coin. 100 cent is equal to 1 euro, or you can say $1. Any whole number of cents of at least 8 cents can be obtained using 3 cents and 5 cent coins. So basically, if we are given any number of cents, for example 8, 9, 10, 11, 12, 13, but at least 8 cents, we can obtain this by using 2 coins, the coins of 3 cents and 5 cents. More formally, we can say this statement as: for all integers n greater than or equal to 8, n cents can be obtained using 3 cent and 5 cent coins. Even more formally, we can say it: for all integers n greater than or equal to 8, p of n is true, where p of n is the sentence. This p of n is, you can say this is a predicate. N cents can be obtained using 3 cent and 5 cent coins. For example, if we have 8 cents, 8 cent can be obtained by 8 cents. 8 cents can be obtained by 3 cents plus 5 cent. There, it's okay. 9 cent can be obtained by using 3 cent plus 3 cent plus 3 cent. 9 cent. 10 cent. If we have 10 cent, we can obtain it by using 2 5 cent coins, 5 cent plus 5 cent. This symbol is sometimes we use like this. We write C and we cross it. This is the symbol of cent. Sometimes we can write it as the symbol is, we can use the symbol for the cents. In the book of Susanna, he has used the symbol C, and he has crossed the C for denoting the cents. If we want to obtain the 11 cents, then we can obtain 11 cents by 3 cent plus 3 cent plus 5 cent. Similarly, we can obtain this number and this number and all the other numbers, all the other cents can be obtained by using a coin of either 3 cent or 5 cent. Now this is basically an example of induction. We have to prove this statement. The cases shown in the table provide inductive evidence to support the claim that P of n is true for general n. Indeed, P of n is true for all n greater than or equal to 8 if and only if it is possible to continue filling in the table for arbitrary large values of n. Means if in the table here we can obtain any number of cents by using 3 cent and 5 cent greater than or equal to 8. For example, if we want to obtain 24 cent by using 3 and 5 coins, we can obtain it easily. We can add up 3 8 times. We can obtain 3 cents 8 times plus so on plus 3 cents 8 times. So 8 3s are 24. So we can obtain any number of cents by using the coins of 3 cents and 5 cents. So P of n is true for general n. Indeed, P of n is true for all n greater than or equal to 8 if we can obtain any number of coins, any number of cents by using the coins of 3 and 8 cents. So how to prove such type of statements? This is basically the you can say intuition to this is basically need to derive some method which helps us to prove such type of statements. So mathematical induction is basically a method of proving such type of statements. For example, what is the principle of mathematical induction? Let P of n be a property that is defined for integers. P of n be any kind of property which is defined for integers, any integer, n, m, anything. Let a be a fixed integer. Suppose the following two statements are true. We suppose that these two statements are true. Then we can say that in general the given statement, the given property P of n is true for all integers. So now what are the two statements? Basically, the initial condition is true. Initial condition is true means for this initial integer a, the property is true, P of a is true, and then for all integers k greater than or equal to a, if P of k is true, then P of k plus 1 is true. If we are succeeded to prove these two statements for the given property P of n, then we can say that the given property P of n is true for all possible integers greater than or equal to a. Then the statement for all integers n greater than or equal to a, P of n is true. So this is basically the principle of mathematical induction. I shall explain it more by giving some examples. First, we need to investigate what are these two statements and how can we prove these two statements. In this we shall discuss method of proof by mathematical induction. Consider the given statement of the form for all integers n greater than or equal to a, the property P of n is true. So this is basically the given property or given statement which we have to prove. Now how we prove it? There are two statements we have to prove. The first is this and second is this. First, the basic step, the first step is also called basic step, and the second step is called inductive step. In first step we have to show P of A is true, as we are given the given property P of n is true for all n greater than or equal to A, means A is the initial integer. You can say that this is basic or starting integer for which this property is true. So first we shall prove that for the initial integer A, this property is true. We have to prove it. Next step, inductive step, is this, that we have to prove this statement: for all integers greater than or equal to A, if P of k is true, then P of k plus 1 is true. This is basically conditional statement, as you can say that for all k greater than or equal to A, if or P of k implies P of k plus 1. As we have discussed in the logic and in the method of proof, first we write the given statement in this form, in this universal conditional statement form. Then we suppose that this is true and we prove the conclusion is true. This is basically the hypothesis of this universal conditional statement, and this is conclusion. We suppose that hypothesis is true, and then we have to prove that the conclusion is also true. So this is all we have to prove for a property to be true for all integers greater than or equal to A. So we prove an example which we have discussed at the starting in the introduction of this mathematical induction. Let's try to prove the given property in the introduction. For all integers n greater than or equal to 8, n cents can be obtained by using 3 cent and 5 cents, 5 cent coins. So first we have to prove the basic property, and we have to show that P of 8 is true, means 8 cents can be obtained by using 3 cent and 5 cent coins. So this is true. Basically, if we use 3 cents plus 5 cents, we can obtain 8 cents. So this is true. And now we have to show that if P of k is true, then P of k plus 1 is true. So as usual, we prove the universal conditional statements. We suppose that hypothesis is true, then the conclusion is true. And in this we suppose first P of k is true, and then we shall prove that P of k plus 1 is true. So we suppose suppose that k is any integer with k greater than or equal to 8 such that k cents can be obtained by using 3 cent and 5 cent coins. So this is basically inductive hypothesis. Then we have to prove the conclusion P of k plus 1 is also true. So there may be two cases here, and we have to prove that k plus 1 cent can be obtained by using 3 cent and 5 cent coins. This we have to prove. We have two cases. The first case is that there is a 5 cent coin among those used to make up the k cents. If this is true, then just replace 5 coin by 3 coins. The result will be k plus 1 cent. If 5 is used to obtain k cents, then we can write k cents is equal to 5 cents plus some other cents. We don't know what are these. If we just replace this 5 cents by 3 cents plus 3 cents plus all the same cents which we have used for the k cents, then this will be k plus 1 cents, because here we have 5, here we have 6. So 6 can be written as 5 plus 1, and 1 is added in this. We obtained k cents, and the remaining 1 becomes k plus 1 cents. Now the case 2 is if there is not a 5-cent coin among those used to make up the k cents. In this case, because k is greater than or equal to 8, at least 3 coins must have been used, because we cannot obtain an integer greater than or equal to 8 by using 3 coins, because 3 plus 3 is 6. So we have to use this integer is greater than 8, because 8 we cannot obtain by using 3 coins or 3 coins. So this integer, we suppose that it is greater than 8. It may be 9, it may be 10, it may be 12 or anything, but it is obtained only by using only 3-cent coins. So there must be at least 3 coins, 3-cent coins must have been used. So if we remove 3-cent coins and replace them by 2 5-cent coins, the result will be k plus 1 cents. How? Because 3-cent coins will give us 9 cents. If we replace it by 2 5-cent coins, we'll get 10 cents. And this is basically, you can think intuitively, and this will give us k plus 1 cent coins. So this was basically the introductory example. To understand better, we take another example, this, which will I hope clear more of your concepts of mathematical induction. If we have to prove this property, for example, for all integers n greater than or equal to 1, 1 plus 2 plus 3 plus 4 up to so on up to n is equal to n into n plus 1 divided by 2. This is basically sum of n integers. So we have to prove that 1 plus 2 plus 3 plus so on until n, this is equal to n into n plus 1 divided by 2. So we have to prove this property. This property basically tells us the sum of n integers. For example, if we want to calculate the sum of first 10 integers, 1 plus 2 plus 3 up to so on plus 10, then instead of adding all these integers, we just use this formula, n into n plus 1 divided by 2. This here we have n is equal to 10, then 10 into 10 plus 1 divided by 2. This will be the sum of all these integers. 10, here we have 5s are, and 11 5s are 55. So the sum of first 10 integers is 55. So this is basically this property of integers. We have to prove this property. First we have to show that p of 1 is true. To establish p of 1, we must show that here basically in the principle of mathematical induction, here the a, for all integers n greater than or equal to a, the property p of n is true. To prove this, we prove the basic step and then the inductive step. In basic step, we prove for the starting integer. Here the starting integer is basically 1. So here you can say that a is 1. So we have to prove p of 1 is true. If we put 1 here, then n is 1, so we stop until first term, because n is 1. If n is 1, then this sum will be until 1. So this is equal to basically 1 into 1 plus 1 divided by 2. So 2 is cancelled out with 2 because 1 plus 1 is 2, and we get 1 is equal to 1. So this property is true because left hand side is equal to right hand side, because 1 is equal to 1 we obtain. Therefore P of 1 is true. Now the second inductive step of the principle of mathematical induction we have to prove. In this case, we, for all integers greater than k greater than or equal to 1, if P of k is true, then P of k plus 1 is true. We have to prove this. So this is hypothesis and this is conclusion. We suppose the hypothesis is true, then we have to prove that conclusion is true. So suppose that P of k is true for a particular but arbitrary chosen integer, any integer k greater than or equal to 1. If it is true, then this whole expression is true for any integer n is equal to k. Means this is true. This is inductive hypothesis. Then we have to prove that the given expression is true for k plus 1. Means P of k plus 1 is also true. Here P of n is basically this whole property. This is P of n. This is P of n. This is basically our predicate. You can say that. As in logic, we have defined the predicates. We must show that P of k plus 1 is true. For that, we must show 1 plus 2, 1 plus 3 up to so on plus k plus 1. This is equal to k plus 1 into k plus 1 plus 1 divided by 2, because instead of n we have used a k plus 1, because here we had n into n plus 1 divided by 2. So instead of n we must have here k plus 1 into k plus 1 plus 1 divided by 2. So we consider the left hand side here, or we have to prove this. Now we have to prove this. We have simplified it. Here k plus 1 plus 1 is k plus 2. We consider the left hand side of this expression. We take the left hand side. Now 1 plus 2 plus 3 until and so on until k plus 1. This is basically 1 plus 2 plus 3 plus so on plus k plus 1. This is true. Now until here we have supposed that this is true. We have supposed that this is true because it's our inductive hypothesis, or it's our hypothesis. And so instead of this 1 2 3 up to k, we can write this. So instead of this written in blue, we can write this. Now this term remains same as. Now taking the LCM of these two terms and then simplifying, we get this, because this can be written as k plus 1 into k plus 2 divided by 2. This is what we have to prove here. So left hand side becomes equals the right hand side by using some calculations and by using algebra, by using factorization here, the simple factorization which you have studied in class 9th and 10th. So we can say that P of k plus 1 is true. So therefore we can say that the basis step and inductive step are both true. Then we conclude that the theorem is true, or you can say the given property is true. The given property is true for all integers. We can say that P of n is true for all n greater than or equal to 1, where P of n is what? P of n is where P of n is 1 plus 2 plus so on plus n is equal to n into n plus 1 divided by 2. this is how we can prove the properties involving integers. By using them, we can prove such type of properties by using principle of mathematical induction. For today, I think it's enough. In the next lecture, we shall continue the principle of mathematical induction 1, in which we shall prove some other properties of integers like this by using this principle of mathematical induction. We shall also discuss the sum of the geometric series and some other topics. We shall also discuss the principle of mathematical induction 2, in which the advanced problems or properties which involves inequalities, we shall try to prove those properties using this principle. At the end, today we have discussed some of the topics of previous lecture, which are change of variable and change of variable in the summation notations and factorial notations. We have started today the mathematical induction, principle of mathematical induction, and how to prove a given property of integers by using this method. These two, finding the sum of sequences, we have discussed it in how to find the sum of first n integers. The sum of geometric series we shall discuss in next lecture. So until the next lecture, Allah Hafiz.